Hello everyone. So in this lecture, in the previous lectures we learned how to do computations using Wick's theorem and Feynman diagrams, and we have done all those computations in real space, like in the space-time coordinates. But when you will go to 3 plus 1 dimension and when you try to do scattering, you will see that it's more convenient to do those computations in frequency space. Okay. So in this lecture, we will try to understand how to do the same set of computations, but now using frequency space. So we will do frequency space Feynman diagrams and the respective computations. Okay. So in order to do that, let's say there is an operator, local operator OT. Okay, and its frequency space expression. So this is true for any operator. Frequency space expression is given by the Fourier transform. Okay, so in general, if you have a bunch of operators at some different times, then for all of them I can individually Fourier transform. So this is from okay. So this is the way we will get the expression for the Fourier space expression for the propagators. So now what about correlators? So let's say there is a endpoint correlator which is of this form. So as we discussed earlier, that we will be only doing frequency time ordered correlation function. So sorry. Great. So then in order to get the frequency space expression, we just take Fourier transform with respect to all these time coordinates. So we have minus infinity to infinity dt1 sorry. And we denote it like in this way. Can just also remove tilde. Okay, so this will be our frequency space correlators. Great. So now question is that how do we compute them? Okay. So so there are several ways. So one is to Fourier transform from position space correlators, but that will be a long way. So Fourier transform position space correlators. Alternative way is to find Feynman rules in frequency space itself. Okay. Examples again. So we start from the simple case of 2-point functions. So this is our this is just the Feynman propagator. Then what about the frequencies? Now we know, so you can do this computation. Okay, and the result is simply the expression for the position space propagator that we already know. Okay, but now the only difference is that here there are two time arguments. And if you do this computation, you know that the Feynman propagator only depends on the difference of time. Okay, since only difference of time, this simply becomes okay. So you see, the distinctive feature is that there is always a delta function. There is a delta function in this case. And the delta function basically comes because of translation invariance, time translation invariance. Because of time translation invariance, the green function only depends on the difference. And since only depends on the difference, there will be always be one or overall delta function in this case. Okay, so it's very easy to prove. Okay, so let's say this is the n-point function. Now from translation invariance, from time translation invariance, this thing is same as right, where t is some constant. Okay, so from this, I mean, this is an exercise. From this, show that the frequency space expression has a delta function. Good. So let's now do some other simple computation. Let's now take up 4-point functions. So again, the position space, so this is some 4-point function. So the position space Feynman diagrams are something like, let's say there are 4 points. So now you see these are all disconnected diagrams, so it's easy to actually do this computation. So in this case we know the expression. In this case the position space expression is simply m comma t1 minus t2 times dm comma t3 minus t4. Okay, which means that when you Fourier transform these expressions, this simply gives us just product of two position frequency space propagator. So this will give us I omega 1 square minus m minus I epsilon square I omega 2 square minus m minus I epsilon square, and then we have delta omega 1 minus omega 2 delta omega 3 minus omega 4. Okay, you can do this computation, check it. It's just simple Fourier transforms. Similarly, the expression for this in the frequency space omega 1 minus omega 4. This will be not 2, this will be 3, I'm sorry. Omega 1 minus omega 4 and this omega 2 minus omega 3. Okay. Similarly also there will be an expression here where I omega 1 square minus m minus let's call it omega 2 square m minus I epsilon square okay. So you can also do some more exercises, but the bottom line is the following. So these are now the frequency space Feynman rules. So now we will directly write down the Feynman rules. Okay. So again, for every local operator, we draw a point. Similarly, lines come out of every point. The number of lines is basically the degree of the polynomial. Okay. Third is that we have to connect the lines in all possible ways. But there is an important constraint that if the operator is normal ordered, remember, then you cannot connect two lines coming out of same point. Okay. Now, fourth is that there will be every line corresponds to Feynman propagators, but now Feynman propagators in frequency space. Every line in frequency space. Now, there is an important part here that for every point, so every propagator will have independent, every propagator has independent frequency. We'll explain it, frequency omega, but all the frequency coming out of a point should add up to the external frequency. Okay, so this is probably too complicated. So let's do this. Let's do this computation. Let's do one simple computation. There will be more exercise. There will be more examples available in the note. So let's say we want to do computation of uh, this thing. Normal ordered. Okay. So how we do that? So let's try to draw that. So okay. So for every operator there will be a point like this, and we denote this one. So we'll do from first step we will do frequency space computation. So we denote it as phi square at omega 1, and this is, let's say, phi square with frequency omega 2. Okay, now there are two lines will come out of it. Okay, and similarly two lines will come off it, and we simply have to glue them like this. Have to connect them. Now I said that every propagator will come with different frequencies. So let's say the frequency of this propagator is omega tilde 1, and the frequency of this propagator is omega tilde 2. Okay, so every propagator comes with its independent frequency. So that was our this rule, fourth rule. But fifth rule says that all the frequency coming out of a point should add up to the external frequency, which means that sum over omega tilde 1, sorry, there is no right, omega tilde 1 plus omega tilde 2 should be omega 1, that's from point 1. And similarly omega tilde 1 plus omega tilde 2 should add up to omega 2 from point 2. Okay, so I forgot to mention here. And then sixth point, all undetermined, for all undetermined frequencies, we have to integrate over them. So then in this case, so let's write the expression. So here we have IH bar omega tilde 1 minus m is not m minus I. Because of this frequency conservation rule, this will be simply omega 1 minus omega tilde 1 whole square. So this is whole square minus m minus I epsilon whole square. And then there will be, of course, a overall delta function omega 1 plus omega 1 minus omega 2, yeah, is equal, yeah. Actually, yes, a better way to actually, for every propagator also frequency comes also with a direction, right? So you have to also come. So in this case, this will be all the things going out. So I write in this way. In this notation, this is the, yeah, this is the way it will be become omega 1 minus omega 2. Now note that the frequency omega 1, sorry, omega tilde 1, it is undetermined. I mean, we have used all the delta functions and everything, and omega tilde 1 is still undetermined. So what we have to do is we have to integrate over omega tilde 1. Okay. So these integrals you can actually do this. sorry, range of integration will be minus infinity to plus infinity. This integral you can do this integral easily, and this integral will become, I think, 1 over m. So there will be always one I will drop out, so I times h bar e square minus 4 m minus I epsilon whole square, and there will be a h bar sitting here. Okay, so logic is clear that so we have to always do this frequency conservation rules. So this I call frequency conservation. And then we have to always integrate over all the undetermined frequencies. I mean, let's review the computation for this 4-point function here again. But now we will do in frequency space. So let's review this frequency space computation again. So we are trying to do, okay, actually let's do, so this will, the details, sorry, this is not, let's do something else. Details is given in notes. Let's say you want to compute the 2-point function of two such operators. Again, we have to two such operators. So how would you do that? There is a point here and there is a point here. So let's say this point, actually let's denote the external frequencies by E. So this is phi L plus 1 E, and this is phi L plus 1. There will be overall always conservation, so we denote it by minus E. So how many lines will go from here to here? L plus 1 lines, right? Okay, so let's denote them omega 1 dot 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 omega L plus 1. But from frequency conservation, so let's say all of them go in this way. So from frequency conservation, we know that omega 1 plus dot 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 omega L plus 1 is E. Okay, so using this relation, then we can get rid of one of these omegas. So there are undetermined, there are undetermined L frequencies. Okay, so we have to integrate over them. Okay, So the details actually you will find in the note. I'm not repeating it here. And you will go through it, and if you have any confusion you can ask me in the interaction session. But so this is how this computation will proceed. Now let me introduce one important terminology. So usually in quantum field theory we say that the number of undetermined frequencies, number of undetermined frequency is equal to number of loops. Okay, so in this convention this is like a L loop diagram. This is a one loop diagram. So, and this is the concept of loop diagrams, where loop diagrams means in that, so loop diagram means that in the frequency space, there are some undetermined frequencies. Undetermined, when I say, I mean undetermined in terms of external frequencies, undetermined frequencies, and we have to integrate over them. Okay, so later when you will do actually perturbation theory, you will see most such applications of loop diagrams, but nevertheless loop diagrams also exist in free theories, and this is what loop diagrams means. So in order to actually understand loop diagram, we have to do frequency space, and in the frequency space we look for the undetermined momentous, undetermined in terms of the external momentous, and then we integrate over them. We always have to integrate over the undetermined momentous. Okay, so this concludes our discussion of loop diagrams. You can consult the note for detailed examples, and in the next lecture we'll get back to scalar field theory in 3+1 dimension.